Good morning and welcome to my final project presentation of variation photography. The world around us is always moving. We're not always cognizant of it, but if we look close enough, everything is always moving and objects are almost always under some forces. A lot of movement happens in the form of vibrations, which we can't always pick up or take apart with our eyes. But analyzing and understanding how objects vibrate can tell a great deal about their material properties, how they would likely move, and so on. In this project, using only video and no other prior information on an object structure or material properties, we wish to understand and extract information on how they move when subject to arbitrary forces. If we have knowledge about the degrees of freedom of an object and the information about the dynamics of an object, we can predict how it will deform on the application of forces. However, in the real world, it's very hard to always have this information. This would, however, be super useful, be it to better understand how bridges respond to stress or just animate arbitrary objects, which would open up a world of endless possibilities in content generation, filming, and augmented reality, and so forth. While we might not have all the information we need above, we can definitely get a video of an object under some forces. If we can extract the motion bases of an object from this video, we can subject it to other arbitrary forces and get an approximate response of the object, from the same. This can help us discover plausible manipulations of the object and how the object will deform on application of different forces. Our project is based on Abe Davis's paper from 2015, which is titled Interactive Dynamic Video. Our work takes inspiration, builds, and combines a few different directions. The first of which is from the theory of vibrations and how vibrations, forces, and object properties combine. The second relates to physically based animation, which uses modal analysis to reduce the degrees of freedom, but often assume some geometric knowledge. The third is motion magnification, the extraction of vibration modes, and how we bring these two together. Vibration modes are usually obtained with actual accelerometers and other sensors on our objects of interest. However, using only video, we can do the same by extracting, by magnifying the motions that already exist in it. On the theory of modal analysis, in order to understand and simulate the effects of forces on our objects of interest, we must relate local object motions, forces, and frequencies of motions we can observe. We can do this by considering the spring equation shown here. The eigenmodes of the system are orthogonal solutions to the generalized eigenvalue problem given by equation 2. And upon making some further simplifying assumptions and solving further, we get the relation relating the quantities we wanted in equation 3. Let's go through our algorithm with the help of an example here. We have three towers here. The first one moves very little in our example. The second one moves a little bit more, and the third moves a lot. So we have actually named them tower 0, 1, and 2. We've picked this example because it demonstrates the effectiveness of the correctness of our extraction and to actually because we know what to anticipate in our simulations. So this vibrated a lot more. Now it's this one, and this one won't actually ever vibrate as much. So first here we see the candidate modes we actually extract. The modes over here correspond to the first tower, which we can see somewhere over here. And the peak, this is the frequency peak that it corresponds with. The second corresponds to this tower, and the third corresponds to this tower, which also correspond to the other peaks. We then take each particular, after extracting the motion basis, we are using the previously derived formula. We simulate and update the position of each pixel using this formula here. Third, we render and project the modal displacements that we calculate with our previous formula into pixel level displacements, which we then further smoothen to actually get the deformations that we actually want. And this is, of course, after applying forces in the previous equation. So going along the results, we can actually see this is an example that goes along time steps. On the first time step we have here, then it moves slightly, then it moves a lot more, and here it moves a lot more. We haven't actually smoothed it to give a better idea of our displacements here. Here we see variations across objects. If we use the same force on tower 0, we see there's very little motion, but when we use it on tower 2, we see that there's a lot of motion. Here we take another example to show the variation with respect to changing forces and location on the same object. Here we have this bridge that's just shaking in a wind tunnel. At force F, we see a certain amount of deviation in location 1, and once we reduce the force by 10, we see a lot lesser deformation. Here we take another object and the same force applied to a different location, we see the deformation pattern is also very different and the amount is different too. And it's the same one over here. When we cut it off, we see very little change at all over here. In terms of the potential improvements and how we can take our project even further, first, we use Gaussian smoothing previously in this implementation, but we can improve it by using object or edge-aware filtering instead. We can also try and improve our overall performance by tying in painting as well, by using some of the newer diffusion models or cans, which we can train and condition with our produced displacement maps, and train in a self-supervised manner, since we actually have the entire video sequences of these situations, which includes future frames. Here are some of the key references for our project, and please refer to the paper for more details, and thank you so much.